Okay, thank you very much for the kind invitation to speak here today. What I want to talk about today is a topic that has arisen multiple times during the sessions, and that's to do with dynamic disorder. So we started a little bit with static disorder, and that's where the localization landscape formalism has been mostly applied so far. But we've also heard that dynamic disorder associated with the phonons in your system can play big roles in the properties of materials, in particular optoelectronic properties of materials I'll be looking at today. And what I want to tell you is our methods and our applications in this realm, and try to convince you that from a purely first principles point of view, so with predictive power, we can actually capture pretty well the role of dynamic disorder. And I think we're at a place where, moving forward, this would be very interesting to link with ideas from the localization landscape to actually be able to do, on the same footing, dynamic and static disorder. And indeed, there were some mentions of this already in Marcel Filoche's talk this morning. So naively, what is dynamic disorder? So if we look at a simple diatomic molecule, like this one here, we have the two nuclei, and we have the electron clouds in the middle, and the molecules are a bond length apart, L naught. Now, in reality, due to both quantum and thermal motion, these nuclei move, and if for the time being we assume this adiabatic approximation, in which the electrons are much lighter than the nuclei, and therefore they move much faster, when the nuclei are at a shorter bond length, the electrons have responded to that, and the cloud in the middle is somewhat denser. And then when they're further apart, again, the electrons respond, and the cloud is somewhat less dense. So this simple pictorial view of dynamic disorder also tells us why it's actually computationally challenging to incorporate in our simulations. And that's because if we don't have dynamic disorder, we have to do a single calculation on the static configuration. But if we have dynamic disorder, we need to understand what happens to the material in all these configurations. And that indeed is related to many of the questions that have arisen in previous talks. So simply put, we want the average over all these configurations. We've seen can be thousands or tens of thousands of configurations. And we need to understand how the property of interest depends on the configuration of the material. Now, I said that it is very challenging, and if you have relatively inexpensive methods, then you can just approach this problem brute force. But if you insist on using first principles methods, like we want to do, to have predictive power, then this just becomes, most of the time, impossible to do. So one of the things we're doing is we're trying to develop methods to help us accelerate these calculations. And in this particular case, what we do is we use ideas from mathematics, in fact, the mean value theorem for integrals, which teaches us that if we want to integrate a function from a to b in red, the naive way of doing that is evaluating that function at many points between a and b, and then averaging over those, and that gives us an estimate of that integral. But the mean value theorem of integrals tells us that we can find some mean value point c, where the value of the function at that point is in fact equal to the value of the integral. And we're all very familiar with this theorem, but this theorem is actually a theorem that proves the existence of such a point, but it doesn't tell us how to construct that point. So in general, that's an unsolved problem. But what we managed to do, in fact, is for the electron nucleus problem, or the electron-phonon coupling problem, we actually managed to find extremely good approximations to this mean configuration, in which it's a representative configuration that captures the same physics as all the potential configurations that the system explores at a given temperature. So this expression down here is, in fact, the exact expression if you make some assumptions as to the dynamics of your system. In particular, we assume that the electron-phonon interaction is lowest order in perturbation theory, and that the harmonic approximation for the lattice dynamics is valid. And then it has this very nice closed form here, which only depends on the frequency of the phonons and the Bose occupation factor. But in fact, we can actually generalize this expression here and also include anharmonic lattice dynamics and higher order interactions in the electron-phonon interaction. The second problem that we have, which also is associated with many of the topics that have arisen, is to do with length scales. And that will connect back to static disorder as well. So when we have dynamic disorder in this case, you can think of this as superimposing some sort of wave on the otherwise crystalline material that you have. And if you only have a small box to simulate your material, then you constrain the length scale that this wave can have. If you want to include longer length scales that are really present in your system, then you have to build a bigger box to do that. And that, again, is computationally challenging. If we want to do calculations in a big box, that's much, much harder than doing calculations in a small box. So this is a second problem that has traditionally hampered using first principles methods to study material properties with dynamic disorder, that is at finite temperature. So again, what we've been doing in the past few years is trying to think of ways around this. And again, we have found some strategies to resolve these problems, in particular under some certain approximations, such as, again, the harmonic or lower decoupling approximations. So here I just have a pictorial view of what we're doing, but essentially what we're doing is a divide and conquer approach, where we replace a calculation on a big simulation box of size 4, in this case, with multiple simulations on smaller boxes of maximum size 4. And we found an exact mapping from calculations in these smaller boxes to the real calculation in the big box, which means that we never have to do these larger scale simulations to capture the dynamic disorder in our problem. So putting this together, what we have done is we have proposed a number of mathematical strategies and computational tools to simplify the way in which we can calculate the role of dynamic disorder in material properties by insisting that we do that at the first principles level, which is traditionally a rather complex problem, many times an unsolved problem. And just to give you an idea of what I mean by accelerating these calculations, so here I'm looking at the system size problem, and this number here is just the size of the simulation box multiplied in the 3 spatial dimensions. And here I'm just, in the last column here, I'm comparing the speed up using the traditional method and using the new approaches that we have proposed. And we see that for relatively small system sizes, we get speed ups of over an order of magnitude, but we can actually reach humongous system sizes of hundreds of thousands of primitive cells. This is an example for crystalline diamond, which are completely impossible to do with traditional methods, but we can actually access them with pretty much the same accuracy. So bearing in mind these developments, what we want to do is we want to study the role of dynamic disorder on electronic observables. Another way of phrasing this is we want to understand how does an electronic observable behave at finite temperature, which is one of the easiest ways of controlling dynamic disorder. And the mathematical problem is pretty straightforward. You just have the expectation value of your electronic observable with respect to the dynamics of your nuclei, which I represent by this chi, and then I have my occupation factor in my standard statistical mechanics averaging. And there are various ways in which such expectation values can be calculated. And indeed, we've seen some earlier today, where, for example, David Belgian was using molecular dynamics in order to study the finite temperature properties of perovskites. And as he actually explained it during his talk, these methods can be very, very time-consuming and many times not applicable to a wide variety of systems. So what we're doing is we've been coupling these developments I've explained with both stochastic and quadratic or perturbative methods to be able to do these calculations in a wide range of materials and with predictive power. So all I've said so far is how do we treat dynamic disorder in our simulations, but then we really want to understand optoelectronic properties of materials. So what I also said is that we want to do this using first principles methods. So what that means is that when we look at single particle properties, we're going to use density functional theory. And for those of you who are not familiar with density functional theory, you can just think of it as a single particle theory, where we have the kinetic energy of the electrons, and then we write the potential in which they move in this fashion. We just have the external potential coming from the nuclei. We have the Hartree potential, and then everything else we just put in this so-called exchange correlation potential. And there is a whole effort trying to find different flavors of this exchange correlation potential. I won't bother about that. All we have to worry about here is that in the single particle theory, there are multiple flavors of it which are better or worse at calculating some properties. But in general, for relatively weakly correlated materials, these methods have relatively good predictive power. We'll actually also be interested in somewhat more complex phenomena, in particular excitons or electron-hole bound pairs. And if you want to study such phenomena, then you cannot use density functional theory like I've just described, because it's a single particle theory. And in order to describe an exciton, which is bound state, you need an explicit two-body interaction. So So when we want to study those phenomena, what we have to do is have to go beyond this density functional theory, and we use something called the Bethe-Salpeter equation, which has this independent particle term, which is, for example, from density functional theory, and then it has this two-particle term, which essentially arises from the two-body Green's function of your system. And writing this Bethe-Salpeter equation in this form is equivalent to saying that your excitonic state is a coherent superposition of electron-hole pairs. So the reason why we're interested in this first principles methods is because they give us the ability to capture excitonic properties. So what I want to do for the rest of the talk, actually, sorry. So what I want to do for the rest of the talk is to look at a number of physical phenomena in semiconductors, physical optoelectronic phenomena, which are essentially driven or largely determined by the fact that we have dynamic disorder in these materials. And what I'll do is I'll focus on the phenomena, and then I'll give examples in a wide variety of materials realizations of these phenomena. Some of them will be inorganic, and some of them will be organic. So the very first one is just perhaps the simplest of all phenomena, which is the bare temperature dependence of the band structures themselves. And I want to show this just to convince you that what we do is it does indeed have predictive power. So what I'm doing here is I'm showing the band gap of a material on the vertical axis as a function of temperature on the horizontal axis. And on the left, I'm showing a relatively simple material, diamond. The red curve are our calculations, and the black diamonds are experimental results. So you can see they're really spot on. And what's interesting is that at high temperatures, we have this linear temperature dependence. And in a sense, that's the classical behavior of the temperature dependence, which is only determined by the Bose occupation factor of your phonons. And then at low temperature, we have this sort of saturation of the band gap. And that's a purely quantum effect. So if we only had classical physics, this linear dependence would go on. This linear dependence would go on and then cross this band somewhere here. And the difference between that and the real result is the quantum correction to this, which in a system like diamond, which is relatively light, is actually quite large. It's about half an electron volt. On the right, I'm showing, again, temperature dependencies of band gaps on a much narrower temperature range around room temperature. The scale here is also much narrower. Again, I'm comparing theory and experiment. But now here I'm looking at a much more complex material, methylammonium lead iodide, which is, again, one of these hybrid perovskites that has come up multiple times during today's discussions. And we have a number of experiments, which are the red and blue triangles. And then I'm showing two theories. So the first one is the dashed line. And that corresponds to using perturbative methods to incorporate the electron-phonon interaction. And you can see that in these more complex materials, those perturbative methods don't do actually very well. They severely overestimate the change in the band gap with temperature. And only when we include higher order terms in the electron-phonon interaction can we capture the proper temperature dependence of the band gap of these more complex materials, which correspond to the solid lines shown in the diagram. So as I said, this is just a very simple thing to calculate. It's just the bare electron energy levels of the system. But then we can start thinking, can we do more interesting things with them? And one of them, for example, is to look at band alignment. So we know that to make use of many optoelectronic properties, we need to interface different types of materials. And this is an example of interfacing CZTS, which is a kesterite material, which is one of the many materials that are being looked at for solar cell applications. It's typically interfaced with something like cadmium sulfide as the transport layer. And what we showed here by looking at the temperature dependence of the band gap, and something I haven't mentioned is that not only do we have to include electron-phonon coupling to capture that, but also thermal expansion, because that's something else that happens in materials when you heat them up. Then the band alignments are actually relatively sensitive to this. And this is something that hasn't really been appreciated very much, at least in this community, but I think in general. And when one tries to design solar cell materials, then it's actually worth thinking about the effects of temperature on these band alignments when you actually perform calculations to try to screen over candidate materials, for example. Another thing that we can learn from the dynamics has to do with, which again has to do with dynamic disorder, is taking us back to the perovskites. So this is a piece of work that we did in collaboration with the experimental people here, led by Felix Deschler. And what we're doing here is we're comparing two perovskites, on the left, we have an inorganic perovskite, cesium-lead bromide, where the cation is a cesium atom. And on the right, we have one of these hybrid perovskites, methylammonium lead iodide, or lead bromide. I can't quite remember whether it's bromide or iodide. It doesn't matter. So what I'm showing at the bottom are the corresponding conduction band minima along some particular path in the Brillouin zone. And what's interesting is that they look very different. And the reason why they look very different is because in the case of the inorganic, the cesium cation is spherically symmetric. And this band here is doubly degenerate. Electrons of opposite spin are just degenerate in energy. What happens in the inorganic, in the hybrid case, is that the methylammonium molecule has a dipole built in it. So that dipole locally breaks inversion symmetry. And because these materials contain lead has strong spin-orbit coupling, and the combination of strong spin-orbit coupling with inversion symmetry breaking leads to a splitting of the electrons of opposite spin. I raise this point because this splitting has been quoted many times in the literature as being one of the reasons why these materials behave the way they do. For example, suggesting that it helps suppress the recombination rate because it creates a slightly indirect band gap due to this Rashburn splitting. Now, Felix Deschler's group were doing experiments, and they were finding no difference whatsoever between the behavior of this inorganic material and this hybrid material, which seems to be contradictory with these band structures that I have here calculated without any dynamic disorder. So what we tried to do next was to try to include the effects of dynamic disorder, and when we do that, that's what we find. So suddenly, the two materials look very, very similar. So if we start with the inorganic material, what we see is that actually this, what used to be a doubly degenerate band, now sort of splits into two branches. And this is, in fact, a type of dynamic Rashburn effect, where the dynamic disorder locally breaks inversion symmetry and induces this spin splitting due to spin-orbit coupling. And the same happens in the hybrid case. But interestingly, the energy scale of the vibration is such that it washes out completely this slight indirect band gap that arose at the static lattice level. And that shows how dynamic disorder takes two seemingly very different materials to behave in the same manner. So that was the first example where I just looked at this very simple property of materials, which is the band structure, which is essentially what we use to build everything else. What I want to do next, I want to look at what happens when we, for example, shoot a photon to the system. And what happens is that the systems can absorb light. So I want to look at light absorption. And I want to look at a few examples in which, again, dynamic disorder plays a crucial role in understanding the optical properties of the material. So the first example has to do with indirect absorption. So I might have a material with the top of the valence band here in blue and the bottom of the conduction band here in red. If I didn't have dynamic disorder, then a transition between one and the other would not be allowed, because when a photon comes in, it brings in a lot of energy, but almost no momentum compared to the size of the Brillouin zone. So that means it only induces vertical transitions. So a photon by itself could not induce a transition from here to here. In order to induce such a transition, I need to provide some momentum, and this momentum can come from dynamic disorder. That's what a phonon rather, does here. So this is just an example of a band structure of an indirect band gap material. This is barium stannate. It's a material that's of some interest for transparent conducting applications at the moment. The reason for that is because it has a band gap here, which is just above the visible, say. And then crucially, it has another big band gap here, such that if you dope this material, placing the Fermi level here, then it can conduct, but at the same time it's transparent because the excitation from here to here and also from here to here are above the visible. So these transparent conductors are very useful. You pretty much have them in all mobile phones, for example. And there is a lot of efforts trying to optimize these materials and find alternative materials that may be cheaper than the present ones. And this is just one such candidate material, and that is band structure. But band structure happens to be indirect, so the top of the valence band is at the R point, the bottom of the conduction band is at the gamma point, and in order to properly understand the optical properties of this material, you really need to include dynamic disorder to be able to bridge this momentum change. So these are some calculations that we did to do that. So if we don't include dynamic disorder, then that's our absorption onset. And if we do include dynamic disorder, either at 0 Kelvin, that means purely quantum motion, or at room temperature, a combination of quantum and thermal motion, then we see there is a huge tail here that we would be otherwise missing in our calculations without dynamic disorder. We can do the same, we can play the same game with other materials. These are just two other examples that we have been looking at, some of them compared with experimental data, in this case boron arsenide and boron phosphide. And one of the interesting things is that we can actually look at the temperature dependence of the onset. And here, again, we compare the static results with dynamic disorder results, and we see this big 1.5 EV difference. And then we see this more subtle temperature dependence over here. And again, a topic that arose this morning was that of Urbach tails, and we think that similar techniques could be used to actually study the much more subtle phenomenon of the exponential decay in this region when you have, say, a direct bandgap material with an Urbach tail. So we're actually very much interested in trying to pursue these ideas along that direction. So a second example I want to discuss where dynamic disorder plays a big role in absorption is to do with dipole-forbidden transitions. So here what I imagine is that I have some conduction bands and then two valence bands, but the first valence band here somehow has a transition to the conduction band which is forbidden by some selection rule. And we'll specify in a moment what that may be. But then again, dynamic disorder to some extent enables that transition to occur. So the example I have here is for cubic indium oxide. Again, this is a material that's being, that actually, the most widely used material actually for as a transparent conductor. And again, you can look at the band structure, you can see clearly why that is. You have a big band gap from the valence to the conduction band, and then if you dope it here, you again have a big band gap to the next conduction band. So the material stays transparent while it's conductive. And this material, like the one I showed earlier, is actually direct band gap. So the top of the valence band is indeed at the gamma point, and the bottom of the conduction band is also at the gamma point. However, if I look at this in some more detail, here I'm just zooming into this region of the minimum band gap. What I'm doing now is I'm coloring the bands according to the parity eigenvalue at the gamma point. What does that mean? This indium oxide structure has inversion symmetry, so that means that parity is an operation that commutes with the Hamiltonian, and at a place like the gamma point, that means that I can classify all the eigenstates of my system according to the parity eigenvalue. And if I do that, I learn that blue is even and red is odd. So the conduction band is blue, and the valence band is also blue. So that means they both have the same parity. And then if I look at the optical matrix element, I see that we have an initial state, a final state, and a dipole operator. And the dipole operator is odd under inversion. That means that this matrix element vanishes if the initial and final state have the same parity. So in this particular case, that's indeed the case. So this has even parity, and so does this. So the transition between here and here is actually not allowed by selection rules. Now, if I do the calculation for absorption in this material without dynamic disorder, this is indeed what I find, and that's my dashed line here. Then if I compare to experiment, I see there is an underestimation of the absorption coefficient of this material by multiple orders of magnitude. So where is this coming from? So again, this is coming from dynamic disorder. And there are various ways in which you can think about this. A sort of real space picture is that as your atoms vibrate, they dynamically break the inversion symmetry of your system and therefore allow that transition to occur. If you prefer to think of this in terms of perturbation theory, then you have an initial state, an intermediate state of opposite parity that is then allowed, and then an intermediate state, a phonon, and the final state of the original parity. So indeed, if we include those dynamic disorder effects, then we find much better agreement with experiment. Again, we can do this as a function of temperature, and again, even at 0 temperature, we have a significant difference from the static lattice result, a purely quantum effect. And we're still somewhat underestimating the experimental results, and that probably comes from the fact that we only include dynamic disorder, but static disorder is not a mechanism by which you could enable these transitions to occur, again, because they break the inversion symmetry of the system and therefore allow those transitions to occur. So probably including static disorder, we would just bridge the little gap left between theory and experiment. Just as another reminder, in all these calculations, although I'm focusing on dynamic disorder, that is the interaction between electrons and phonons, temperature also has another effect, which is that of thermal expansion. So here I'm just showing an example of what happens in this particular case due to thermal expansion. So what we do is we calculate the temperature-dependent volume by minimizing the free energy of the material at a given temperature, and then we can also look at the changes, say, in the band gap as a function of purely thermal expansion. And typically, they can be up to the same order of magnitude as the electron-phonon interactions, depending on the material. So we always have to include them. Okay, so up to this point, I've been discussing single particle theories. So we've only been looking at exciting a single particle electron up to the conduction band. But we all know that when you excite an electron, many times it can form a bound state with the hole that's left behind. And this is very important in many situations. One of them is luminescence, where you're considering the recombination of electron hole pairs. Again, if we're interested in looking at something like recombination in indirect bandgap materials, then we need to provide the momentum mismatch through some mechanism, and again, dynamic disorder is what would enable us to do that. So the example here is hexagonal boron nitride. So we're looking at the 3D version of hexagonal boron nitride. At the moment, the 2D version is also very much of very much interest, but here we're looking at the 3D version, which happens to be an indirect bandgap material. So the bottom of the conduction band is at the end point, and the top of the valence band is close to the K point. And this material actually has a surprisingly large luminescence, despite the fact that it's in direct bandgap semiconductor. So we're trying to understand how that came about. And our hypothesis was, well, this is probably driven by some phonons that couple to the excitons and allow you to bridge this indirect gap here. So we calculated the phonon dispersion of this material, and we identified the phonon momentum, which is shown by this vertical red line, that has a momentum that exactly matches this difference between the K and the M points that would allow us to bridge this indirect excited state. I also want to point out that if you look at this particular phonon wave vector, you see that there are multiple energies of optical and acoustic longitudinal transverse phonons. So what we did then is we did one of the very first ever calculations of exciton-phonon coupling purely from first principles. And what we had to do actually was we had to extend the ideas of this Bethe-Salpeter equation that I've explained earlier, which is usually used for absorption processes, to recombination processes to study luminescence, and that's something called the out-of-equilibrium Bethe-Salpeter equation. And if you just do those calculations, you get the exciton lines here, but you don't see any signal because it's in direct bandgap material and you don't get any luminescence. What we then did was we used perturbation theory in this case to make the calculations feasible, to calculate the change in the matrix elements due to having phonons in your system. And then these are just conservation of energy rules and phonon occupation factors. And by doing that, what we found is the blue curve here, which compares to the experimental orange curve. They're just arbitrarily offset for ease of comparison, so these are arbitrary units. But what's important is that at the nominal value of the excitonic energy, we see nothing. But then offset from it, we see a number of resonances. And you can identify each of these resonances with the phonon frequency that we had in the band structure earlier, in the phonon band structure earlier, at this particular vector. So these give you the offsets, and these correspond to the LOTO, LATA, and so on phonons, and they are in very good agreement with the locations of the corresponding resonances in the experiment, and we also reproduce quite well the relative sizes of these peaks. Now, what all the other phonons in the system do, what the rest of the dynamic disorder does, is just gives you the width of these peaks. So the final example that I want to look at is again looking at excitons and the interaction of excitons with dynamic disorder. And in this particular case, we're going to look at another case where excitons play a fundamental role, and that's in organic materials. So in inorganic materials, exciton binding energies are relatively small because the screening is very large, and therefore the electron-hole interaction is largely screened, so they're weakly bound. But in organic materials, the screening is much weaker, and therefore the electron-hole interaction is much stronger, and you can form strongly bound excitons. So we're looking at the canonical canonical organic semiconductor has featured many, many times today already, which is pentacene. And down here I have two pictures of the structure of pentacene, where I draw the exciton wave functions, and in particular I draw the singlet exciton wave function and the triplet exciton wave function. And what I want you to notice is that the triplet exciton wave function is pretty much localized around a single pentacene molecule, whereas the singlet exciton wave function spans a number of molecules. So the localization character of these excitons is very different. And what we find is that this has enormous consequences for the coupling of these excitons to the phonons in the system, which one way of measuring that is looking at the temperature dependence of these excitons, and that's what's being plotted here at the top. So let me start with the singlet exciton. So what we have here is we have this dotted line, which is the temperature dependence of the exciton energy level arising from exciton-phonon coupling. Then we have that dashed line here, which corresponds to the temperature dependence of the exciton arising from thermal expansion. And then we have the solid line, which is the combination of both. The one I want to focus on in this talk is actually the exciton-phonon coupling. And you can see that if you compare that between the singlet and the triplet, you see that the singlet has relatively strong temperature dependence, whereas the triplet has pretty much no temperature dependence. Now, why is that? That's because at temperature we're looking at here from 0 to 400 Kelvin, the phonons that are exciting the system are low-energy phonons, and these correspond to crystal phonons in the system. So these are phonons that change the relative position of the different pentacene molecules in the crystal. So such dynamic disorder in the system will greatly affect an object like the singlet, which is delocalized over many such molecules, but won't do much to an object like the triplet, which is sitting in a single molecule, and therefore it won't really care much about the relative position of other molecules. So that was the hypothesis of how we have an interplay between the localization properties of these exciton wave functions and the dynamics of the system. And to confirm this, we looked at another member of the asyn series, naphthalene, which happens to have both singlet and triplet excitons, which are very much localized around a single molecule. And indeed, in this case, we find that the temperature dependence arising from exciton-phonon coupling in both cases is very, very similar, in line with their localization properties. So this is actually a very interesting story, and we've extended these results to all the asyns. And this is actually work being led by Antonius Albertis here in the audience, and he has a very nice poster downstairs. So I encourage all of you to actually go and check out his poster. And he's much more knowledgeable than I am about all of this. So I encourage you to go and learn more about this, talking to him. So to summarize a little bit what I've just said, I hope I've convinced you that from a purely first principles point of view, we have a good handle at the moment on treating dynamic disorder in semiconductors and on their optical properties, optoelectronic properties. And what we've heard throughout this meeting is that static disorder also plays a major role in the properties of semiconductors. And what we really would like to do is to be able to treat both dynamic and static disorder on the same footing. And that's where I think that ideas from the localization landscape could really come to fruition. And we already heard earlier this morning Marcel Filoche explaining some ideas about combining, having the effects of phonons on the localization landscape to be able to hop between different localized basins in there. And we think that the ideas that we have been exploring from first principles could also be combined with this and hopefully help us study all of this phenomena on the same footing. So I'll probably finish. I had a few more slides just to highlight that we can actually use these methods to do many other things like topological materials, NMR, and things like that, but I'll just skip that for the sake of time, and I'll just finish by acknowledging all the collaborators and brief summary of what I've discussed. Thank you.